So hello again. Tonight we're going to talk about the unmanned, uncrewed Global Hawk surveillance aircraft and how that might be a good interim until the next major project for far infrared astronomy, now that SOFIA is no longer funded and is being hung up in a museum. The Spitzer Space Telescope has gone warm and lost its funding and is no longer operating either. So we have kind of a gap and that we can't see in far infrared, and we'll discuss how that actually works. So I was on the final of the NASA SOFIA teletalks on August 23rd, and the title of the presentation was SOFIA and the Future of Infrared Astronomy. And they were trying to, for the people that are aware, describe what infrared is and the various bands of infrared, the major bands of infrared, near, medium, and far, and how SOFIA was the only game in town left observing in far infrared, and had to explain how those instruments are different. They have to be cooled to within less than 1 Kelvin, very, very cold, and how, all those other telescopes you hear about, like James Webb and Euclid that was recently launched to L2, they're near infrared and mid-infrared, but they don't get down to far infrared. So we lost the ability to observe in far infrared. And while they said, yeah, we could probably do something in the short term using sounding rockets, these are rockets that are not anywhere as large as, a Falcon 9, and they go up in kind of a parabola and then come back down. So they don't spend a lot of time in the upper atmosphere. But that's a cheap way to get an instrument up there. But you only spend a few minutes at the top of the arc at your peak altitude. And that's probably not enough good observing exposure duration for infrared. Then they talked about the pressure-controlled helium-filled balloons that they fly over the Antarctic. The balloon launch itself is not that expensive. The instrument that they launch, which can be like a ton and a half, is far more expensive than the balloon and the helium that they put into it. But you can hang around up there for about a month. The balloon actually rotates in an orbit at about 70,000 feet above the Antarctic. The cost is getting everyone down there, getting all the equipment and the helium down there for the balloon launch, and then monitoring it, having people staying down there to monitor it while it's pirouetting around the South Pole, and then having it land, and then sending the guys out to recover it, because the instrument's too expensive to do a one-time. So the balloon disconnects and it parachutes down, and then they recover the instrument and refurbish it and reuse it. So, the launch itself of the balloon is not that expensive, but the project cost is just as much as if you were launching a rocket. And then they spoke of rockets, smaller rockets that launch CubeSats, nanosats, and picosats to low Earth orbit. The thing that you launch only lasts for a few years, and then it falls back and burns up and is not reusable. And you have to plan in advance what instruments you're going to use, your launch, your commitment to what you're going to observe. All that becomes essentially fixed at the point of launch. And given how small the satellites are, you're not going to put up a large aperture telescope into a CubeSat. And if you remember, almost a year ago, I did a presentation on the guy that hand grinds the mirrors for CubeSats and how small, how small these mirrors really are. And that's not really great for far infrared. And then you need a power source to maintain the very low temperatures, the less than 1 Kelvin temperatures, to keep the instrument cool. And you just don't have that level of power source on a small satellite. But since it's a rocket launch, it's just as expensive as launching a satellite. So you do a share the ride kind of thing where your satellite isn't the only one that gets launched by the single booster. The single booster might launch 30 to 100 satellites. So your satellite can't take up a lot of space or consume a lot of power. And then somebody said, well, we can do ground-based infrared observing. That's true. At the near infrared and a little bit into the mid infrared levels, not at all in the far infrared, because the water vapor in the Earth's atmosphere absorbs all the far infrared wavelengths. So one of the things they had to do was, as I said, dispel the misconception of infrared is just one big homogeneous band, and therefore anything that can do infrared can do all bands of infrared. And it's broken down into basically 3 bands. The near infrared, you can think, your TV remote control, or that irritating infrared that you have to put a filter in, otherwise your mobile phone camera will be overexposed too easily. The mid infrared, this is kind of the resistance heat of your old style stovetop burners, the electric burners, where you can't see all the heat that's coming out because some of it's invisible infrared. But you can buy a camera adapter for your phone or a dedicated camera that can see in that wavelength of infrared. Doesn't require any special cooling, and it's pretty inexpensive. It's getting it above the Earth's atmosphere where the money comes in. And then there's the true far infrared. These are very low energy, which means you have to have very much cooled instruments to see it. The Spitzer Space Telescope had 2 phases, one of which, when it was cooled, that's the cool period, it could do far infrared. But then as its helium eventually leaked out, it became the Spitzer Warm Space Telescope and could do near infrared and medium infrared, but could no longer do far infrared. Eventually, Spitzer could no longer do far infrared, so that became, okay, what can we do in far infrared with? SOFIA. But now that SOFIA has ended, we don't really have anything that can do far infrared. Now here's the level of cooling. If you think of normal astronomy cameras, you might want to put a Peltier chip on there to cool it down to where you can get rid of the electronic heat noise or the noise interference in your imaging. And the same is true in radio astronomy. But when you want to get to very, very low levels of energy, the photons in far infrared, your instrument's normal electronic warmth would basically negate your ability to do observing in far infrared. So you've got specialized instruments that will get you down into the medium infrared, and James Webb only gets down to medium infrared. It can't get down into far infrared. And it uses what is known as a mechanical cryocooler. No helium, so it's going to stay mid-cold longer than Spitzer did. If you're helium-based, then eventually over time, you're going to warm things up as the helium finds gaps and microscopic gaps in welds to reduce the helium pressure, and therefore you can't keep it cool. So I've got 3 columns here at the bottom: Fahrenheit, Celsius, and Kelvin. And you can see the freezing point, and then absolute 0 is near where you want your far infrared instrument operating. So you're down around minus 460 degrees Fahrenheit or minus 273 degrees Celsius, which is 0 Kelvin. So if you were just a fraction above that, you'd still be over 460 degrees below 0 or 260 degrees below 0 Celsius. Very cold. So we talk about this gap. At the moment, we have all sorts of observatories and spacecraft and instruments that can see in gamma and X-ray and UV and visible and near infrared and medium infrared. And then at the bottom, we have all sorts of radio wavelengths with big antennas and small antennas, and people doing software-defined radio as amateurs. But we have this gap between microwave radio and mid-infrared, and that's where far infrared is. At the moment, we're kind of missing that. Absent SOFIA and the Fifi and the Hawk instruments, we have no far infrared capability to observe. But who really cares? It's far infrared. It's a part of infrared that we can't see in. You can't see real infrared at all. It requires instruments. What difference does it make? Well, there's a whole lot of physics and chemistry that are transitions from visible to near to mid through far into microwave, that we have basically a gap there now and we can't see what goes on in there. We have astronomy in the forms of low energy actions in accretion disks that form planets and moons, and interstellar gas clouds that are expanding or condensing, and all of that kinds of stuff is in the very coldest low energy wavelengths, which is far infrared. Having no instrument that will allow us to observe in far infrared is kind of like, hey, there was a tree. I went into the forest, there was a tree. I came back, the tree was laying on the ground. What happened to it? You can look at evidence like, hey, it's got a burn mark at the base, must have been lightning, or it's got, insects that got into the trunk of the tree, and so they ate through and the tree fell over. But did wind cause it to break over? Was it the force of rainwater? You don't know because you weren't there to observe it. The same kind of thing is true in astronomy. Things can happen in far infrared, and if we have no ability to observe it, that's a gap. So what was it that SOFIA did for us? Well, for those people that aren't aware of SOFIA, it was a modified 747 SP. That's the shorter, not 400 passengers version of the 747. And they created a bump towards the back end of the fuselage, and they put in the back a non-pressurized chamber, and they put a shutter over the bump. And inside there, they had a very large infrared reflector type of telescope. And they had instruments that were cooled by liquid nitrogen to the first stage, and then to the next stage down, liquid helium as a two-stage cooler, so they could do far infrared. The 747 could fly at more than 40,000 feet, which is above 90+% of the water vapor in the atmosphere. So it did a really good job of far infrared astronomy. And it could operate for different parts of the sky, different times of the year. It could operate from California and then fly down to Christchurch, New Zealand, and fly out of New Zealand for a part of the year. And NASA's decadal survey said, who needs far infrared? And they looked at the operational cost when SOFIA wasn't performing missions and said, it's not worth the cost. So they removed the funding, which literally allowed it to drain out and shut down. So no more SOFIA, no more far infrared. Well, if you look...
There was another thing that SOFIA did that it was impossible for any other observatory to do, is do shadows of planets crossing in front of stars. So the transit, SOFIA could be launched anywhere in the planet. So we could see the atmosphere of Pluto passing behind the star. We could see eclipses or something other that happened on the sky that was just a specific area of the planet, and no other observatory can change place like that.
And in the next couple of slides, we'll get into the pluses and minuses of the SOFIA program. And one of them was the dynamic nature of its instruments. It could swap instruments in and out, but also the dynamic nature of its flight plans, where it could, fly from Southern California all the way up into Canada, out over the Pacific Ocean, and then back down in one evening flight. So they could observe a lot of different things just in one flight. Most of that was not in far infrared. It was in mid-infrared. Some of it was photographic, and some of it was spectroscopic. So it was a very flexible capability. If you look back at the history of the NASA airborne astronomy aircraft that existed before SOFIA, there were 3 of them. They started out with, they picked basically a private jet and said, let's see what we can do with this thing. And then they said, this is great. Let's make it bigger. So they picked a bigger airplane and they put a bigger telescope in it, and they got even better results. And then they said, let's get some dedicated money. So they got dedicated money for the SOFIA program, and so created a big, costly program because the science was focused on infrared. A lot of the times, other observatories, other instruments would do the lion's share of that work. And so SOFIA was left to only doing the stuff that it was unique for. And there wasn't enough of that to justify the amount of money it cost per year to keep the program running. But the prior programs produced enough beneficial, unique results in infrared that because they were cheaper to keep, not only could they keep going, they could actually broaden the program. So I think what really needs to happen is the program needs to shrink down a notch. The technology's gone up, shrink the program cost down a notch, and you can probably continue to do it for the foreseeable future, but you've got to find the right vehicle, the right aircraft for the job. So if the total program cost is truly the issue with SOFIA, and you still want to do far infrared science, you've got to find a way of doing it less expensively. And you've got to look at every aspect of the program to really shrink down the total program cost. Well, there are these things called Global Hawk. This is a picture of one. They're a jet turbine aircraft. They're very efficient. They fly very high, 50,000+ feet, so higher than SOFIA. You can fly them from a normal airport. They can fly around for 1 month without refueling. So they're very efficient. You can see how long and wide the wings are. They're very efficient at their flight pattern. So you can take off from a normal airfield, fly it around at 50,000 feet for up to a month at a time, and then land it back down. And also you can change out the instruments. Now, it's a spy plane. It's an Earth resources plane for NASA. So it looks down at the Earth, not up into space. But they've made a lot of changes. NASA's made a lot of changes to it in order to do the instruments that they wanted to do. Now, they're not in far infrared, but there are some in medium infrared because you'd like to be able to look at things at night on the ground, and they produce heat. This is already a vehicle being used by NASA. There's no people on board. It's uncrewed, unmanned. They fly it. It's not autonomous. You have to fly it. But it's an active program in use by NASA for Earth resources. So let's look at the pluses and minuses. Here's SOFIA's pluses and minuses. Yes, it was stratospheric. Great for infrared. It could fly overnight missions. Great. It had a 2.5 meter aperture telescope. Really great. You can see fine details that way. The instruments were dynamic. You could decide what instrument you wanted to fly, put it on board the plane, fly it for a mission, come back down, take out that instrument, put another one for the next flight. It could do both optical and spectroscopic observing. Because it had the engine power of a 747, there was a lot of electricity that was available. So you could run lots of instrumentation, cryo coolers for far infrared observing. And because it was a 747, it was one of the shorter ones, it could land at pretty much any large commercial airfield, take off from the same place. And also, if you had to do some work on it, pretty much any hangar where you could do work on a 747, you could use it in that hangar. But they had dedicated hangar for it in Southern California at the Dryden/Armstrong Research Flight Center. But it's a long duration aircraft, so it could fly from Southern California to Canada and then back again, all in a single overnight flight. Now for the minuses. It's a big aircraft. Maintenance is expensive for engines that are that large. It wasn't, like a brand new airframe, so they had to occasionally replace rivets and sections of the airframe because it had seen so much use. There were people on board. There were all sorts of people on board. There was the aircraft flight crew, the astronomical instrument operations crew, the principal science crew for whatever projects they were doing, and then the essentially the SETI airborne astronomy ambassadors, the STEM kind of observer crew, the educational crew. All of those people on board the airplane are a cost of the program. And really, it's a matter of safety risk to people. You have to have additional aspects of the program because you're risking the lives of people on board. So you have to take that all into account. You need the ground and maintenance crew to keep it up to specifications. It literally took about 2 years to qualify a new instrument to fly on SOFIA, not because of the instrumentation technology, but because of all of the power and safety requirements that you had to put it through in order to qualify it, in case it is, let's say, cryogenically cooled, and you don't want it exploding on board a plane that has people on board. So you had all these extra bells and whistles and gates you had to go through in order to qualify an instrument. Supposedly, the operational costs weren't matched with the scientific results, but it was a niche instrument. There were things only it could do, and with Spitzer gone by more than a year earlier, it was the only game left in town for far infrared. But the decadal survey said, we're not getting enough out of it and it's costing us too much money. So they pulled the plug on its funding and literally allowed the money to run out and shut down the program. So sorry, no more SOFIA. Looking at the Global Hawk, what are its pluses and minuses? Well, let's see. It's a stratospheric instrument. It has the ability to do flight schedules. It can linger for a month over a target. So more than just overnight. And you only really want to do infrared overnight. Very good for doing the overnight flights that SOFIA did at the same range. Dynamic instruments. It has an instrument bay. You can open up the instrument bay, take instruments out, put instruments in. It was known when doing Earth resources observing for NASA, you could, swap instruments during missions. It has a jet turbine engine, which is good for creating a lot of electricity for your instrumentation. It has a very long wingspan. If your airfield is capable of that width of a wingspan, which is only 116 feet, it can be used at most airfields that can support, if it can support a 747, it can support a Global Hawk. Use all the same hangars, but we'll get to it in a moment. NASA already has a hangar for it. There's no people on board the aircraft. This greatly reduces the cost, the prep, and the safety risk. Because there's no people on board, it reduces the operations crew size. So instead of having people that maintain the instruments on the ground and in the air, you can have the same people that maintain the instruments on the ground, operating the instruments from the ground. Maybe it's worth exploring as an interim project before the next congressional approval funded, $1 billion far infrared program project, whatever that might be, if it does. And it would make a perfect instrument testing platform for any future space-based far infrared instruments. Since they're cheap enough, because they're not a full size like 747, instead of having one plane that flies between California and New Zealand, you might actually be able to afford 2 all year long planes that can fly out of, one from California, one from New Zealand. The minuses are, if you make it too big a project, if you put too many bells and whistles on it, too many gates for it to cross, instead of it being a pimple that's invisible, it becomes a sore that becomes visible to Congress, and Congress won't give you the massive funding. So you got to keep it cheap. The instrument and communications packages currently point down at the Earth, even for the Earth resources, let alone the spy missions. So they would have to create instruments that look up. Currently, it uses military communication satellites for its communications. You'd have to switch that over to civilian satellites if you want to have a non-militarized program. Just as commercial airliners are now starting to support Starlink for internet access, you could put a Starlink terminal in the Global Hawk and have it point up. Instead of having the big satellite dish in the nose, you could have a flat plane antenna behind the nose and still do satellite communications. But you're going to have to create a new instrument program to make the instruments smaller, maybe use mechanical cryostats, but those take a while to cool down. You might want to go back to the nitrogen and helium for smaller instruments for just overnight flights. But if you're thinking you can't do anything with a smaller aperture, the Galax, WISE, and HiRISE telescopes are all less than 1 meter aperture, and they do science with those, including some in the near and mid-infrared. So a larger aperture is not necessarily directly related to the far infrared wavelength. It's more related to getting finer details in whatever you're imaging. Since the Global Hawk is something that people on the ground fly, there has to be direct radio communication between the pilots on the ground and the aircraft in the sky, which usually means for surveillance that some people on the ground are within radio range of the aircraft for flying it, but that the satellite communication is for surveillance data. Well, if you're using Starlink, you could be anywhere on the planet and do the same sort of thing. And since you're up high in space, there aren't any trees or clouds to get in your way that would be normal obstructions for Starlink. Somebody did ask about this one, vibration and tracking. If it's on board an airplane, isn't there some kind of an issue with, getting the telescope to point at a target and then track it for long duration exposures for imaging and spectroscopic analysis? SOFIA did this. Much larger, heavier telescope. It was mounted in a floating oil bearing to minimize engine vibration. And when the telescope was observing, the telescope tracking electronics actually flew the aircraft to keep the mirror stable. The plane would move, but the mirror would be tracking something. So you can do the same thing for this. But if you think about it for a moment, the Global Hawk, in its prior life as a clandestine surveillance camera, already does this, because from 50,000+ feet, it had to observe people and vehicles on the ground. Very tiny things for long periods of time. It had to follow them around. So I think they've already got the issues of vibration and tracking. They know how to do that with the Global Hawk. But if you're thinking, I don't know, this is going to be a whole new program for NASA. Au contraire, NASA has been using Global Hawks for some time for Earth resource monitoring. They have 2 Global Hawks at the Dryden Armstrong base already, but they already have 2 and they're getting a 3rd one. The first 2 were like early production models of the Global Hawk called Block 2, and they've got a 3rd one in the pipeline that they should have by now. It's a Block 10. So there's 10 generations of Global Hawk that CIA, NSA, and the military have already improved upon. Lower cost of operation, less maintenance, longer flight times, longer linger times, easier to operate, all those kind of things. But what they have not done is put missiles on it, because the smaller drone aircraft, they put missiles on those because they fly much lower. Having to fly at 50,000+ feet with missiles that you're going to launch from that level, it's not quite as effective. But we'll get into that in a moment. But what I did find interesting was they wanted to do a science program called ATREX. It was a tropopause. This is the final layer in the troposphere before you get up to the next layer. And they wanted to do atmospheric observations, and they could fly the Global Hawk that high. The Global Hawk could already fly to the troposphere. And the weird thing was they had to put the flight crew, the pilots, at Guam, because the place they wanted to fly the Global Hawk was over the Pacific Ocean. So they flew it out of our Air Force base out of Guam with the pilots in a trailer in Guam to fly it, because it had to be within radio range overhead. But for Southern California flights, they solved this problem. They actually created a Armstrong Global Hawk Flight Operations Center in Southern California. So if they got another Global Hawk for a different mission that wasn't being done at exactly the same time, there'd be no problem. They've already got the budgeted staff in place, the equipment, the data communications. It's all there. So the cost to crank up an airborne astronomy program with a Global Hawk, the price just keeps falling down and down and down. And they're actually using them as hurricane hunter aircraft, because they're jet, they can get to the scene and fly for longer periods of time than the manned hurricane hunter aircraft. So what about the smaller guy? What about the Predator? The Global Hawk is the bigger bird, flies higher. The Predator, the B model, also known as the MQ-9 Reaper. Gotta love the names the military gives it. It's an autonomous drone aircraft. You tell it what to do, and it goes and does it. And while it's up there, it can have a couple of missiles hanging under the wings. And then if you want to go decide to take out a bad guy, somebody corroborates, decides, and then just tells the Reaper, Fox 2, and launches a missile at the target. It can carry heavy things. It can fly around for a while, but it's oh so much smaller, because it has to be able to pack up in the back of a trailer and take it out to some out in the middle of nowhere site and fly it from there. People that program it know about it, but they're not really pilots because they're not actively flying it. They program a mission into the Predator, and it goes off and flies the surveillance mission or the linger and wait for a missile launch kind of mission. But it's smaller, and because it has a propeller, it's a turbine propeller. You can see the turbine inlet on the back. It's not going to have the level of electricity available to it that the Global Hawk will. But if we want to just, prototype the concept, and they're cheaper than a Global Hawk, maybe it's a starting point like those earlier aircraft before SOFIA. Maybe they can do a small infrared telescope adapting from looking down to looking up on a Reaper. So you might start there, but if Global Hawk makes sense, forget the Predator. It's too small. You're not going to get the power budget you need, and you might need more power or reduced weight for this thing, and that would make it less effective. So if you can go for the Global Hawk, because many things are already in place, go for the Global Hawk. But here's the other interesting thing. You got to look at the bigger picture. Northrop Grumman, in its clandestine spy aircraft work with the U.S. government, remember he's saying there was a Block 10? There are newer Global Hawks and newer things beyond the Global Hawk program that are coming out. But what is the NSA and the CIA and the Air Force or Space Force going to do with all of the Global Hawks they already have in flight missions? Those become unused aircraft. And NASA likes to repurpose unused aircraft as the other missions that are clandestine go into either newer model Global Hawks or completely different new aircraft that are autonomous. That means that Global Hawks come up as available. If that's the case, there could already be a Global Hawk sitting around in a hangar just waiting to be converted, which reduces yet again the cost of migration. The program's cheaper, the operations are cheaper, there's no people on board the aircraft. Yeah, the instrument's smaller, but if you make it out of one of these, it can probably last a lot longer than SOFIA has, and it'll probably be a NASA-only program because it comes out of Northrop Grumman and spy satellite, spy surveillance planes, so wouldn't want any foreign governments helping us out on that. If you can create a cheap-to-keep program, maybe this can get off the ground pretty quickly. I'm not an aircraft designer. I'm not an astronomical instrument designer. All I can do is hope to communicate concept basics to people that are more appropriate, like the movers and shakers, the funding people, the NASA instrument people, operations people that operate the Global Hawks, the people in the U.S. military that are working with SpaceX Starlink to do Starlink communications for the military. Get all those people together in a room, get them involved, and go, what would it cost for us to crank one of these things out just as a prototype? Well, let's see. You're obviously going to have to rework the instrumentation and communications. Power source is available. The operations folks are available. The equipment for flying it's available. If you put it out there as grab the last of the not flown SOFIA far infrared missions, scale them down for the reduced aperture, create a new Fifi or a new Hawk Plus that would fit on board a Global Hawk, and just repurpose those science missions for a prototype of a far infrared airborne instrument. But you've got to scale back the program in order to make it something that wouldn't become a budgetary burden, incite the ire of the decadal survey folks for, we thought we killed this thing off. If you ever learn about the space shuttle program and the fact that we killed off the space shuttle program because there were people on board, look up the X-47B. It's a smaller scale space shuttle, complete with the opening doors that can put things up in space. Those have been known to fly for over a year at a time because there's no people on board. It's a lower cost program that can do all the things that were really needed that were lost capabilities once the space shuttle no longer flew. Well, a Global Hawk, as a scaled back program, could be a far infrared airborne astronomy instrument that could pick up where SOFIA left off for a scaled back set of observations. But you've got to realize that if this thing is piloted by people on the ground, then your principal scientists are going to be remote, they're not going to be on board the aircraft, just like they are with any other big observatory. If I'm an astronomer in Chicago and I want some observations done by a telescope in South America, I'm not going to get the budgetary funding to fly down to South America in the hopes that it'll be able to observe what I want when I told it to do it. It could be atmospheric conditions. It could be equipment failures. They'll do it when they get to it, but I don't need to be down there for that. Just send me an email with the attached files as the results once you get it done. Same thing can be true of a Global Hawk far infrared astronomy program. You put it in the pipeline of the science queue. When it gets done, we send you the results. You can still have a SETI-based airborne astronomy ambassadors program. They just won't be on the plane. They can still be a part of the program, learn about it, broaden the minds of those that don't know about it, do the educational programs that they did after the flights anyway. And instead of going through third parties for all of the public communications, I know NASA knows where Zoom is. They can do much cheaper outreach programs via Zoom than the multiple tiers of paid contractors that they use for things like teletalks or WebEx conferences. They know how to do it cheaper. They do it cheaper when they decide that they need to. You got to keep it cheaper. Otherwise, it'll stand out too much. And if it's small enough and all the facilities are there and the aircraft are there, it's literally just the cost of the instrument conversion and then the time of the flight operations. So it's possible to scale this back considerably, and that could make it a reality. So in conclusion, SOFIA had unique capabilities that are already being missed. The prominent one of that was far infrared observing. Prior to SOFIA, they did repurpose existing stratospheric airframes. We can do that once again. SOFIA did have modular instruments, had programmable missions, and they flew out of existing aircraft facilities. We can do that again. I would say instead of the infrastructure cost of using the military communication satellites, a couple $100 a month, go with Starlink. With no people on board the aircraft, that's a huge savings in operations and flight safety. And just operate the science programs as if it was a remote observatory. They already know how to do that. The astronomers and the astrophysicists already know how to do that, and it lowers the cost. So the next generation of unmanned mini SOFIA, kind of like the X-47B is a mini shuttle, without a crew on board, without the additional staff, cut its costs back, make it the next interim far infrared deep space observing program until you get the big budget money. Just think about it, consider it. I think there's some things you can work with. And of course, I have links. And if you want to know about the Global Hawk as produced by Northrop Grumman, and then down below the General Atomics Predator Reaper, we've got that, and then how NASA uses both of those, and then SOFIA as well. Comments, questions?
How big is the front of the Global Hawk?
You can get a 0.8 meter diameter mirror in there, so it's less than 1 meter.
Okay.
Whereas SOFIA was what, 2 meters?
2.5.
2.5, yeah. But remember, NASA did have a 10-inch Newtonian telescope on board. What was it, a DC-10?
Learjet.
No, after the Learjet.
DC-10.
DC-10. They had two DC-10s.
They had two.
Yeah. So if the plane's cheaper and the program's cheaper, you can have more than one of them.
And the thing that I didn't know that it's in your presentation is that it can be for a longer time, about a month, right?
It can fly away, what they call linger for a month.
Linger.
But since
yeah.
it has to be with the radio range of the pilots, it does a lot of circling, a lot of large diameter circling. But SOFIA never flew a mission longer than overnight because it was infrared. When the sun came out, you can't do infrared.
No, and not just that. The autonomy of the airplane is 10 hours safety. In safety, 10 hours.
Right. So a Global Hawk would be able to do that standing on its head.
Yeah, so in that case, it could be a smaller telescope because if you can linger, you can gather more data. You
Yep.
can actually even move the airplane and do like artificial interferometry and
Yep.
simulate our larger telescopes doing that. So that I'm impressed. A
Yeah.
month like on flight, that is it gives a long time like for capturing the same image and you keep going just like you have like those deep fields from Hubble.
Yep.
You could do the same if you can linger that long
No,
in the same place. That's amazing. That
one
can
of
be done
one
like
of the
for a station. Now I see that can be done.
yeah, one of the downsides of Sophia that weren't considered a downside, it was just an aspect of the airframe and the flight program. When Sophia wanted to observe a target, it had to be understood whether the target was on the left side of the airplane, the port side, or the right side, the starboard side. Because if it was on the port side, they could do it as the plane flew north to
Yeah.
Canada. If the target was on the starboard side, you had to wait until it would fly up to the north terminus, turn around and fly back, and then it would look out the other side of the airplane. Because
Yeah,
the
and the other
telescope
thing.
could only tilt up a certain number of degrees because the hole was only so big.
Yeah, no, and then you have to wait also for the right time. In that case, you have depending on the objects and depending where, because we work normally on winters,
Mhm.
because winters you have more hours of
Mhm.
nighttime. So in that case, you have to wait for the right time of the year where the object would be in the area where the angle where Sophia would take the data. So it depends the time of the year and it depends also the flight. So when they did for the whole year, whatever people were flying to take pictures, they organized the flight path by the whole year. So then you're gonna be in this mission that's gonna happen in April, and the next guy, no, your mission is this object is gonna be better visible in a better angle for Sophia in December, or depending on the time of the year, and because Sophia works better during the winters, when they start adding the New Zealand missions, it was excellent because it doubled the time of the mission instead to be, not functioning during the summers.
The other thing to think in the history of stratospheric infrared astronomy is when they did the first program out of a Learjet, they took one of the existing windows and removed the glass and made that the aperture. So it was always on the side of the airplane. When they did the
Yes.
PC-10, it was out the roof of the airplane. So they had a broader view of the sky. Well, this would bring back the broader view of the sky because it would be out the roof of the Global Hawk. And think about imaging astronomy when things are low on the horizon versus overhead.
Yes, much
There's
better.
less atmosphere to look through, so you're going to get a better image. So
Right.
there's a number of pluses you get for going with the telescope pointing out the top and for having an aircraft that is cheaper to operate. And you might even be able to have more of them. And you can
Yes,
fly
they
it whenever
get
you
like
need it.
a interferometry. It would be simulate a huge telescope.
Well, what would really be cool is if you could have a couple of them so you could be flying one out of California and one out of New Zealand.
It's not worth it, Monroe, because if you go from one or the other, one is going to be summer, one is going to be winter. Depending on the latitude, you would have only a few hours of that darkness, so it's not worth it.
It is worth it because it's a global hawk
Unless it just
and
stays there and
it
waits.
does not need to fly directly over New Zealand. It can fly all the way up to Japan if it needs to, and then back. So the idea of having the two of them would be one is for the northern hemisphere objects and one is for the southern hemisphere objects, and that doesn't change throughout the year. There are
Yeah.
things that are in the south that you just can't see from the north and vice versa. For those of you out there, once this thing goes public and are listening, give it some thought. I think there's something here. I think
Yeah.
is.
I was a doubter in the beginning, but yeah, it's very convincing.
I took what I
really
knew.
good
I took what
idea.
I knew of Sophia, and I took the comments that you had given me over my first proposing it when I learned that Sophia was going to lose budget, and I said I've got to find an answer to every one of these questions, and I just kept finding this ought to be a lot cheaper than starting from scratch, a lot cheaper, because NASA's already using them. NASA already has them. There's one's becoming available.
I think both of the DC-3 had accidents, and actually a lot of people die, or maybe one. I
One of
remember
them
one
did.
of them.
One of them did. Yeah.
Yeah, and Learjet's still in the hangar and still
Yes.
in use.
Well, I hope the right people listen to us.
Well, of course, it's just my opinion. I could be right. Okay. Any comments before I stop recording?
Crickets.